Hey Math 20-2s, today we're going to look at radical equations. So step one, let's look at some restrictions on values of the variable in a radical expression. Let's consider the radical expression square root x. On the grid, sketch the graph of y equals square root x. So if we think about values for x, x cannot be negative. We can't take the square root of a negative number. So the first number we take the square root of is 0. So the square root of 0 is 0. And the square root of 1, when x is 1, y is 1. And when x is 4, the square root of 4 is 2. So y is 2. And when x is 9, 5, 6, 7, 8, 9, maybe about there, the square root of 9 is 3, so y is 3. So this would be the graph of y equals the square root of x. State the domain of the graph. Well, like I said, we can't take the square root of a negative number, so our domain should be x such that x is greater than or equal to 0, and x is any real number. Three, for what values of x is the radical expression square root x defined? So now we're talking about what makes this a real value, not an imaginary number. So that would be a lot like the domain restriction. X must be greater than or equal to 0. If x is negative, we can't take the square root of that, so it becomes undefined. Part B. Consider the radical expression the square root of x minus 2. On the grid, sketch the graph of y equals the square root of x minus 2. So if you think about what's happening here, we're shifting this graph 2 units to the right, and we're drawing the exact same graph we did up there. Move 1 over, the square root of 1 is 1 up. The square root of 4 over, 1, 2, 3, 4 over is 2 up. The square root of 9 over is 3 up. So it's the exact same graph we drew over there, but we are now shifted 2 units to the right. So that's the graph of y equals the square root of x minus 2. Part 2, state the domain of this graph. Again, this graph goes forever right, but it doesn't go anything past x is 2. So x such that x is greater than or equal to 2, and x is any real number. For the radical expression, square root of x minus 2, state the restrictions on x. Alright, so that's like saying what values for x are defined. Same thing, state the restrictions on x. It means the same, means answer the question the same as we did up there. So in order for this expression to be a real number, we have a value of x that we're going to have to restrict the values for x to make this into a real number. So it's a lot like this domain again. X must be greater than or equal to 2. If x is less than 2, we're going to get a negative number inside the radical sign. We know that's undefined. We can't take the square root of a negative number. All right, so explain how to determine the restrictions algebraically. What we're going to do is we look at the value of the radicand, which is what's underneath the square root sign, and make sure it is never positive. Sorry, make sure it is never negative. So if I did it for this one, I would say x minus 2 must always be greater than or equal to 0. All right, that has to happen for this expression. We look at the radicand, which is x minus 2, and it can never be negative, so it must be greater than or equal to 0. Now, that would be a decent restriction. If I want to solve it for x, I simply add 2 to both sides. So x must be greater than or equal to 2. So there's our restriction. All right. Part C, consider the radical expression 3 minus 2x, and take the square root of that. On the grid, sketch the graph of y equals the square root of 3 minus 2x. All right. So if you went to your graphing calculators, what you would notice is this thing has an x-intercept of 1.5, and this graph would move across to the left. All right. So it would look something like that. That's the graph of y equals the square root of 3 minus 2x. State the restriction of the variables in the radical expression. So let's look at this thing. 3 minus 2x must always be greater than or equal to 0. All right. So if I want to solve that equation as an inequality, I'm going to add 2x to both sides. So I get 3 is greater than or equal to 2x. And I divide both sides by 2. So 3 halves is greater than or equal to x. Or if you want to write it the other way around, x is less than or equal to 3 halves. So I've just done part 3, determine the restrictions algebraically. There they are. X is less than or equal to 3 halves. All right. Note, radical expressions involving square roots may have restrictions on the value of the variable because the square root of a negative number is not defined. That is very true. All right. Let's look at a radical equation then. A radical equation is an equation which contains a radical. A value of the variable which satisfies the equation is called a root of the equation. In this lesson, we will solve radical equations involving one radical graphically and algebraically. One of the techniques involves factoring quadratic equations. Example number 1. Algebraically determine any restrictions on x in these radical equations. So if I'm looking for restrictions, I'm not trying to solve the equation. I don't need to know what x is to make this equation true. I'm just looking at the radicand, what's underneath the square root sign, and seeing what values x can possibly be. Remember, we can't have a negative sign under the radical sign. So I would say x minus 2 must be greater than or equal to 0. All right? The radicand can never be negative, so x minus 2 must be greater than or equal to 0. Or if I add 2 to both sides, my restriction is x is greater than or equal to 2 for part A. For part B, look at the radicand, what's underneath the radical sign, and make sure that radicand, 4x plus 1, is greater than or equal to 0. That's how you find the restriction. So now I'm going to rework this inequality, solve it for x. So I'm going to minus 1 from both sides. So 4x is greater than or equal to negative 1. And I'm going to divide both sides by 4. So x is greater than or equal to negative 1/4. There are your restrictions. All right. For part C, again, look at the radicand. What's underneath the radical sign? Nothing else matters when we're talking about restrictions. And whatever's underneath the radical sign, it must be greater than or equal to 0. We can't have a negative number under there. So now let's solve this inequality. It's a little easier if we add the x's and always try and keep positive x's. But if you wanted to keep the x's on the left side, then I'm going to minus 2 from both sides of this inequality. So I still have a negative 5x is now greater than or equal to negative 2. And I now have to divide both sides by negative 5. And if you do this, you find out that x is negative 2 divided by negative 5 is positive 2/5. But anytime you divide both sides or multiply both sides of an inequality, this says greater than or equal to, that's an inequality, you must reverse the sign to make sure this stays true. All right? So put a big star beside this one. Maybe say, remember to reverse the sign. Part D. We've got a cube root of x minus 1. So if I'm looking for restrictions on the value of x, can you take the cube root of a negative number? And if you can answer that question with yes, then you would say there are no restrictions. And yes, we can take the cube root of a negative number. So x has no restrictions on it. That's also true for any odd number index, right? So cube roots, fifth roots, seventh roots, 9 roots, and so on. They will have no restrictions because you can take cube roots and fifth roots and seventh roots of negative numbers. Not true for square roots or fourth roots or sixth roots or eighth roots. Those will always have restrictions because you can't have negatives underneath the radical sign if you have an even numbered index value. Example 2. Solve some radical equations graphically. All right. Consider the radical equation square root of x plus 1 equals 4. State the values of x for which the radical equation is defined. So they're talking about restrictions. So underline your radicand and make sure that radicand value is never negative. Must be greater than or equal to 0. Minus 1 from both sides. So my restriction, or the values for x which make this radical equation defined, are x is greater than or equal to negative 1. All right. So just like we did up above, we're just worried about not having a negative under the radical sign. Those are called restrictions. Those are called values for which the radical is defined. We can't take the square root of a negative number. Part B. Explain how to use a graphing calculator to find the solution to the equation by using the intersect feature on that calculator. Well, here's what you're going to do. We'll write it out and then we'll actually do it on the calculator. So in your y equals screen, you're going to let y1 equal the left side of this equation, square root of x plus 1. In y2, you're going to let y2 equal the right side of this equation, which is 4. You're going to graph these in an appropriate viewing window. Our calculator gives us a viewing window. If you're doing this on a written response question, you should state that window. In this case, our window for x looks like it's going from -3 all the way to 20. So minimum -3, maximum of 20 by a scale of 1. And our window for y looks like it's going from -5 to +5 by a scale of 1. So once you're done graphing that, you then go a second function, and above the trace button, you see the word calculate. So you go second calculate, and you go down to number 5, which says point of intersection or intersect. All right, so we're going to do that right now. Okay, so go to your graphing calculator, go to the y equals screen, type in the left side of this equation, the square root of x plus 1. Press enter. In y2, I'm going to type in the right side of the equation, which is 4. You'll notice that left of my y2, I've got a little darker line drawn, so when I graph it, I can see what's going on. Hit your window button, and let's make the window the same as in our workbook. So x has a minimum of -3 and a maximum of 20 by a scale of 1. And y goes from -5 to +5 by a scale of 1. Now if we press graph, there is the left side, square root of x plus 1. Here's the right side, y equals 4. Follow along, go second, calculate, down to number 5, which says intersect, and follow the on-screen prompts. What is the first curve? Well, the first curve, the cursor is highlighting on it, y1. That's good, we press enter. What's the second curve we want to use? Well, that's the line y2 equals 4. Cursor's highlighted on that, press enter. Do we need to make a guess? No, there's only one point of intersection, so just press enter again. And there is our point of intersection, x is 15 when y is 4. All right. So if I want to draw these in our notebook, all right, here's y2 at 4. That's y equals 4, and y1 was thinner, and that started right here, and it went about like this. That's y1 equals the square root of x plus 1. We found the point of intersection to be at 15. So number C says, oh there, it gives us the window setting. Great, matches up with our calculator. So label display the graphs on the grid above, so we've done that. Very nice. Now state the solution to the equation. Well, the solution to the equation is x equals 15. Verify the solution algebraically. So when it says verify, we substitute back into our original equation and plug in the solution. So square root of x plus 1, well, we just found out x to be 15. Square root of 15 plus 1 should equal 4. Square root of 16 should equal 4. Yes, that's a true statement, so we verified it. All right. Great. Let's go to investigation number 1. Solving radical equations algebraically. Complete the following steps to solve the following radical equation and verify the solution. So the square root of x plus 1 equals 4. Step 1, square both sides. So whatever I do to one side of the equation, I can do to the other. If I square both sides of the equation, things look good. The square root of x plus 1 all squared means this radical sign is going to be gone. So squaring a square root eliminates the radical sign, and 4 squared is 16. Now, pretty easy equation to solve. I simply minus 1 from both sides, and x equals 15. Verify the solution. Again, 15 plus 1 should equal 4. The square root of 15 plus 1, and we know the square root of 16 indeed equals 4. So we verified it. So the method of solving a radical equation by squaring both sides of the equation needs to be studied in a little more detail. Let's see what happens if I look at example 2 here, investigation 2. Complete the following steps to determine the roots of the radical equation and verify the solution. So let's solve 3 plus square root of x minus 1 equals x. So the step 1, they're trying to isolate the radical, so they're going to move the 3 to this side by subtracting 3. They're now going to square both sides to eliminate the radical sign. So square root of x minus 1 all squared is x minus 1. X minus 3 all squared, well, we know how to square a binomial. That's the same as saying x minus 3 times x minus 3. So x times x is x squared, minus 3x minus 3x is a minus 6x, and negative 3 times negative 3 is a positive 9. Well, when you get this type of an equation, you want to set the equation equal to 0. So I'm going to move the x's over there, and I'm going to move the 1 over there. So I'm going to keep my x squared. I've got a positive x here, so I'm going to minus x from both sides. So negative 6 minus 1 is a negative 7 x's. I'm going to add 1 to both sides. 9 plus 1 is 10. Opposite of negative 1 is plus 1, so I'm going to add 1 to both sides. What you now have is a quadratic equation. 0 equals x squared minus 7x plus 10. How do I solve this equation? Well, you have to remember back in grade 10 when we factored. So this is really a simple trinomial. We learned how to factor simple trinomials in grade 10. You ask yourselves, what two numbers have a sum of negative 7 and a product of positive 10? If you can figure out what those numbers are, then you know what the factors are. Those numbers are minus 2 and minus 5. Negative 2 plus negative 5 adds to negative 7, and it multiplies to positive 10. What you do now is factor this trinomial. So the factors of x squared minus 7x plus 10 are x minus 2 and x minus 5. And our rule now says if this statement is equal to 0, then either factor can be 0. 0 times anything will equal 0. So x minus 2 can equal 0, or x minus 5 can equal 0. As long as one of these brackets is 0, we're going to get 0 times some number, and 0 times any number is 0. So this will remain true. And now these are pretty simple equations to solve. X minus 2 equals 0, we'll add 2 to both sides. X minus 5 equals 0, so you add 5 to both sides. So our solutions are x equals 5 and x equals 2. Verify this. So we've got two solutions we have to check. So let's check at x equals 5. All right, so you go back to your original equation, which is right up here. 3 plus the square root of x is 5 minus 1 should equal x. X was 5. So 3 plus the square root of 5 minus 1, which is 4, should equal 5. Square root of 4 is 2. 3 plus 2 equals 5. Yes, that's a true statement. So this one verifies. That's very nice. Let's also check when x is positive 2. So let's try this one. 3 plus the square root of 2 minus 1 should equal 2. So 3 plus the square root of 2 minus 1, well, that's 1. And the square root of 1 is 1, so 3 plus 1 equals 2. 4 equals 2. Not true. All right, that is not true. So we would call this extraneous solution. All right. So we've done everything correct. You haven't made any mistakes over here in our math. We solved it correctly, we factored correctly, we got correct solutions. We check one of them, that works out really nice. But when we check this one, it doesn't work. And sometimes when it doesn't work, you get an extraneous solution. Extraneous solution. And that's what happens when you introduce the exponent 2 to this equation. Right? So sometimes when you square it, you introduce solutions that aren't really there. Now if you solve this graphically, right, if you solve this equation graphically, you will never ever get any extraneous solutions. When you solve it algebraically, you must always verify, because there are some times you get solutions that are not true. If you solve it algebraically, you have to check. If you solve it graphically, you will never ever have extraneous solutions. So let's quickly solve this equation graphically. Right? If I want to solve it graphically, I will let y1 equal 3 plus the square root of x plus 1. And I'm going to let y2 equal x. So let's do that. Go back to our y equals screen, clear these two equations. In y1, we're going to type the left side, 3 plus the square root of x minus 1. Sorry, it's x minus 1. X minus 1. And in y2, we're going to type in the right side of the equation, which was x. And let's get a window setting that makes sense. So if you just did your standard viewing window, zoom 6, 10 by 10. Let's see if that's going to work. Looks like there's only one point of intersection there. So let's go second calculate. The point of intersection number 5. In this case, the first curve is highlighted, but there is no cursor on that curve. So move your arrow to the right until you get a y value on the bottom, or until the cursor shows up on the curve. Great. Once it's there, you can press enter. Second curve, well, it's blinking on the line. That's great. Do you have to make a guess? No, you only have to make a guess if there's more than one point of intersection. There's only one point of intersection in this equation, and that occurs when x is 5. So that also satisfies the equation we had here. The only true solution was x is 5. All right. All right, let's turn to the last page, extraneous roots, extraneous solutions. In investigation 2, one of the solutions can be verified, but the other one cannot. Can you explain why solving a radical equation by squaring both sides of the equation can lead to an invalid solution? The answer provided in the section below. So here's why it happens. The process used in solving investigation 2 led to an answer which was not one of the roots of the original radical equation, or of the radical equation in step 1. It is, however, a root of the non-radical equation in step 2, formed by squaring the original equation. So when we squared the equation, we got a new equation, but it was no longer a radical equation. It was a non-radical equation. This is because the process of solving a radical equation is based on squaring both sides. If two quantities are equal, then the squares are equal. The converse, however, is not necessarily true. Two quantities which have squares that are equal are not necessarily equal quantities. For example, negative 3 squared is the same as positive 3 squared, but it's definitely not true that negative 3 equals positive 3. That's not true. So that's why when you square a radical equation and get a non-radical equation, you may introduce some extraneous roots. So in general, the process of squaring may lead to an answer which doesn't satisfy the original radical equation. This type of an answer is called an extraneous solution or an extraneous root. It is always necessary to verify the solution to a radical equation if you solve it algebraically. There will not be any extraneous roots with radical equations where the radical index is 3, because each number has a unique cubed root. So let's complete the following work to determine the extraneous root of the square root of x plus 2 equals x. So we've isolated the radical. That's step 1. Get the radical all by itself on one side of the equation. Step 2, you're going to square both sides. As soon as you do that, you may introduce a solution that's not true. So you square a square root, you just get the radicand. X times x is x squared. We now have a quadratic equation. It's no longer a radical equation. To solve a quadratic equation, you must set the equation equal to 0. So I can move everything over to the right side. I'm going to minus x from both sides. And I'm going to minus 2 from both sides. So we now have a quadratic equation we can solve by factoring. So you make your two sets of brackets. The only way to get to x squared is to put an x in the front. Ask yourself what two numbers have a sum of -1 and a product of -2. Those two numbers are -2 and +1. All right. And like we said before, you now let each factor equal 0. So x minus 2 can equal 0, or x plus 1 can equal 0. And you solve those simple equations. Here we're going to add 2 to both sides. Here we're going to minus 1 from both sides. There are our solutions. Let's now verify them. So let's do a quick check. At x equals 2, let's see what happens to this equation. The square root of x plus 2 should equal x. The square root of 4 is 2. Yes, 2 is 2. Checks out. This is a good solution. Very nice. Let's find out what happens if we check when x is -1. So the square root of -1 plus 2 should equal -1. And -1 plus 2 is 1. The square root of 1 is 1. -1 does not equal 1. This is an extraneous root. All right. Solving radical equations algebraically. So use the following method to algebraically solve a radical equation if the radical has an index number of 2. Step 1, isolate the radical. Get the square root sign all by itself on one side of the equal sign. That's what that means. Then square both sides of the equation. Solve the resulting equation, which is going to be a quadratic equation. We're going to probably solve it by factoring, just like we've done the last couple examples. And then if you're solving it algebraically, you must verify every single solution you get and check for any extraneous roots. So solve the following radical equations. A. Isolate the radical. Well, it's already isolated. The square root of x plus 3 equals 7. Next up, let's square both sides. So you square a radical, you get the radicand. 7 squared is 49. Pretty simple to solve this one. Minus 3 from both sides. We've got our solution. Do a quick verification. All right, the square root of x, which is 46, plus 3 should equal 7. 46 and 3 is 49. The square root of 49 is indeed 7. Checks out. We've got a good solution. All right, let's look at part B. Step 1, isolate the radical. So let's get rid of the 7 from the left side of the equation. So I got the square root of 49 minus x will equal x minus 7. Now that I've isolated the radical, I can square both sides. So if you square a radical, you get the radicand. The squared, x minus 7 all squared. Square the first term. So that's going to be x squared. Multiply two terms together and double it, so that's minus 14x, and square the last term. -7 times -7 is positive 49. Now what you want to do is set the equation equal to 0. So I've only got one set of x squareds. I'm going to add x to both sides. So I get -14 plus 1 is 13x. And I get a minus 49 from both sides. So 49 minus 49 is 0. So I've got something called a baby quadratic. It's only got two terms. So to factor this one, I'm going to use common factoring. The common factor of these two terms is x. So I divide both terms by x. I get x times x minus 13. Same thing's true. Set each factor to 0. So x can equal 0 or x minus 13 can equal 0. Well, this is already one of the solutions. The other solution would be adding 13 to both sides of this equation. You get x is 13. Well, we're not sure if they're good yet until after we verify them. So let's do a quick check. If I check and see if when x is 0, so at x equals 0, I've got the square root of 49 minus 0 plus 7 should equal 0. So square root of 49 is 7. 7 plus 7 equals 0. That is not true. 14 doesn't equal 0. So this is not a good solution. It's extraneous. All right. Let's see what happens when we plug in 13. The square root of 49 minus 13 plus 7 should equal 0. So this, we're going to find out when x is 13. All right, so 49 minus 13 is 36. Square root of 36 plus 7 should equal 0. Square root of 36 is 6. 6 plus 7 is 0. 13 doesn't equal 0. So another extraneous root. So both of these don't work. I would say for this equation, there are no solutions. We checked them both and nothing worked. No solutions for this equation. All right. Use the method of use the algebraic method to solve the radical equation that has an index of 3. So let's try this last one. So step 1, isolate the radical term. So I've got the cube root of 2x minus 7 would equal, I'm going to add 5 to both sides, so 0 plus 5 is 5. I'm now going to cube both sides of this. So to get rid of the cube root, I'm going to cube both sides. So the cube and the cube root cancel out. I'm left with the radicand, 2x minus 7 equals 5 cubed, which is 125. And now I simply add 7 to both, add 7 to both sides. So I get 2x equals 132, and divide both sides by 2. So x equals 66. All right, let's check and make sure that works. So the cube root of 2 times 66 minus 7, subtract 5, should equal 0. So the cube root of 2 times 66 is 132 minus 7 is the cube root of 125. Subtract that from 5 should equal 0. The cube root of 125 is indeed 5. And 5 minus 5 does equal 0. So this is a good solution. Excellent. You guys have your work assigned numbers 1 through 13. Let's get after it.